Hello everyone. In this particular lecture, we shall be discussing about some mathematical functions that will be of extreme importance in physics. Let's begin with the most elementary function, which is the equation for a straight line. So here we have a straight line that is passing through the origin in a Cartesian coordinate system. Where this is the x-axis and this is the y-axis. So since this line is passing through the origin, the equation of the line will be given by f of x is equal to x. The most general form of this line is going to be of the form f of x is going to equal to mx plus c, where this m is going to be called as the slope and the c is called as the y-intercept. In our case, since we have the equation f of x is equal to x, the slope m is nothing but equal to 1. Now, another way of looking at the slope is basically it's the tangent of the line. So, if the slope is nothing but tan theta, theta is basically this angle, then tan theta is equal to 1, which implies theta is going to be equal to 45 degrees in our case. So this angle is equal to 45 degrees. Now, suppose you have a line which is passing at an angle with a different slope. It might appear to you like this. In this case, the slope will be equal to this angle theta, or tan theta is equal to delta f by delta x, delta f by delta x, where delta f is small change in the function as x changes through a small distance delta x. So tan theta in this case is going to be equal to delta f by delta x, which is nothing but equal to the slope. This c, which we have seen here, is nothing but the y-intercept. So y-intercept is this distance. So this distance is going to be equal to c. Intercept. Now let's go to the next important function, which is going to be called as the parabola equation, which has this particular form: f of x is equal to x squared. Now this is a symmetric function. Now what do you mean by a function being symmetric? By definition, if f of minus x is equal to f of x, then this function is going to be called as symmetric function. And if f of minus x is equal to minus f of x, then the function is called as antisymmetric. In our case, since f of x is equal to x squared, if I substitute f of minus x, that is going to be equal to minus x whole squared, which is equal to x squared, which is same as that of f of x as we defined here. This function is going to be a symmetric function. What it physically means is that it is symmetric about the y-axis. So it is like a mirror reflection about y-axis. Okay. Now, the important things to notice about in this particular function is that the minimum value of the function happens here, which is nothing but the point corresponding to x is equal to 0. As a homework, what you have to do now is basically you will have to find out what will happen if you had a function which goes like f of x is equal to 4x squared, or if you have a function like f of x is equal to 4x squared plus c, if you had an equation of this form, what would have happened? Same way, you can also think about if you had a function like f of x is equal to 4x squared plus 3x plus c, then what would have happened? These kind of plotting can be easily done on online platform, which is you just have to Google search for Wolfram Cloud. So if you Google search for this particular site, this is a site where we have a basic software that can be accessed by all of us, called as Mathematica. So all of you should create an account in this Wolfram Cloud and use the facilities available there to plot these functions and then see what are the changes which is going to happen to the parabolic equation. Also, you should try to guess what will be the equation if the parabola was an inverted parabola, which might look like somewhat like this. Or if you had a parabola like this, what would have been the equation for that particular parabola? Okay. These are also part of your homework assignment. Now let's look at another function which is seldom used in physics, but for completeness sake, we are going to do this. This is the function f of x is equal to x cube. Now, if you notice this particular function, this is going to be an anti-symmetric function. How do you know that? You substitute f of minus x, that is going to be equal to minus x whole cube, which is going to be equal to minus x cube, which is nothing but identical to minus of f of x being x cube. This is the condition which is required to satisfy an anti-symmetric function, and hence this function is going to be an anti-symmetric one. Why is the symmetric nature and the anti-symmetric nature is important for us in ordinary physics is basically very often when you have to perform an integration of the function, this concept of symmetric and anti-symmetric functions are extremely important. For example, if you perform the integration of this particular function from, let's say, minus x to minus 4 to plus 4, then you will see that without actually performing the integration, you can actually show that the function has to be equal to 0. Because the area under the curve is basically, suppose you are integrating from, let's say, 2.5, minus 2.5 to plus 2.5, the area under the curve will be basically this plus this area. Now, in such a situation, you'll see that if this area has positive value, this area will have negative value. So sum of these two areas will work out to be equal to 0. So if you have a function which is antisymmetric and the integration is going from minus some x to plus x, then you will see that sum works out to be equal to 0. So whenever you have a function, first thing what you have to note down is whether the function is symmetric or antisymmetric. Now here is another function which is f of x is equal to x to the power 4, which also apparently looks like that of a parabolic curve. But please notice one thing, as it is plotted, it looks as if in this region the value of the function is 0, but it is not true. The function's value will become equal to 0 only at x is equal to 0, okay, nowhere else. So even though you see plots, you have to be very careful about analyzing the plots. I just wanted to show that. It will be quite interesting for you to check whether this f of x is equal to x to the power 4 lies within x squared or outside of x squared. What I mean is whether this function will be something like this, or whether the function will be something like this. It is interesting for you to check. If you do a quick glance, you will see that when you have, let's say, the value of minus 2, the value corresponding to this one out here, where this curve intersects it, will be at about 16. Okay, minus 2, this intersection point is going to be at 16, whereas for a parabola, minus 2 will correspond to plus 4, somewhere here. So naturally, f of x is equal to x to the power 4 should be lying within this. So this could be x to the power 4 possible. Okay, so that is something which you have to check. Now let's move on to some trigonometric functions. The first function which you should be very familiar with is sin x. The sin x, what I have plotted out here is from 0 to 2 pi, as you can see, but sin extends from minus infinity to plus infinity actually. So it goes somewhat like this, and here it might go somewhat like this, and then repeat it. The second function which you have to look at is basically cos x. Now cos x, what happens is that again I have plotted from 0 to 2 pi. At 0 the value is maximum, which is equal to 1, and then it comes to 0 at x is equal to pi by 2. In the case of sine, what is happening is at x is equal to 0, you are starting with 0 value. It reaches a maximum value as pi by 2. In this case, cos, at pi by 2, the value of cos is equal to 0, and at pi, it will have maximum negative value. Whereas in the case of sine, at pi, the value works out to be equal to 0. Now, let's look at the third function. The third function is quite interesting, which is basically the tan function. The tan function looks somewhat like this. Although I have plotted from 0 to pi, 2 pi as before, tan also extends in the negative domain. It might look somewhat like this in the negative domain, negative x direction. Another important thing for you to notice about tan function is if I draw a line like this through pi by 2, you will see that the tan function approaches this line but doesn't touch this line at all. Tan function touches this line at plus infinity or minus infinity, as the case may be. If I extend this line backward, it will intersect this line at minus infinity. Such kind of lines are going to be called as asymptote to this function at at infinity. And in our case, there is a jump from plus infinity to minus infinity for a slight change around pi by 2. This kind of phenomena is going to be called as a discontinuity. And this is actually going to be called as a infinite discontinuity, as the value jumps from plus infinity to minus infinity in a extremely short span. Now, I'll expect you to use the Mathematica software or go to Wolfram Cloud and try to plot secant x, cosecant x, and cot x. Please plot these functions and see how these functions look like. It will be quite interesting. Now let's move on to the next important aspect, that is sin x. Now I have explained to you what is sin x earlier. Now if I ask you to plot sin 2x, the plot will look like this. What happens out here is, if you observe carefully, in the first case I had plotted from 0 to 2 pi, and there is a single sine curve lying in this range. But when you have sin 2x in the range 0 to 2 pi, there are two sines now. If I break it into two pieces like this, you will have the first sine here and then the second sine, as you can see here. Now let's plot sin 3x. Sin 3x will look like this. Now again, the range is from 0 to 2 pi, as you can see here. But now if I break it up into pieces, there is one here, second piece here, and then the third piece. So what is happening is in the same range 0 to 2 pi, you have three sine functions. Now you'll be able to generalize what is the meaning of sine 4x, sine 5x, etc. So that I leave it as a homework for you. Exactly in the same way, you should try to plot what is cos x, cos 3x, cos 2x, cos 4x, etc. and then see what happens. Now, this kind of functions are extremely important when you study something called as Fourier series, either in mathematics, physics, or electronics. This is of extreme importance. This Fourier series basically tells us that any periodic function which satisfies certain conditions, called as the Dirichlet conditions, uh, can be decomposed or broken up into sines and cosines. Okay, so sines means could be in terms of sin x, sin 2x, sin 3x, etc., or cos x, cos 2x, cos 3x, etc. Any periodic function has this particular behavior. This you might study only in your third or fourth semester in physics, but when you study that, please remember what is the physical meaning of sin x, sin 2x, sin 3x, etc. Now, let's look at another very important function, which is an exponential function. The typical exponential function shape is given here, e to the power minus x. Notice one thing, uh, at x is equal to 0, the e to the power minus x has got a value which is equal to 1. Usually in physics, we will be plotting only in the first quadrant. So often in textbooks, you will see only this region. This is going to be called as an exponential decay. It's an exponentially decay curve. And this becomes very important. This function is of extreme importance in when you study radioactive decay or decay of charges in a capacitor, etc., etc. Okay. So please remember what is the shape of e to the power minus x. Now, in the negative direction, you notice that the e to the power minus x actually increases exponentially. Now, in the same way, let's look at e to the power x, which looks somewhat like this. So it looks like a mirror reflection of the e to the power minus x about the y-axis. And it's also having the value 1 when x is equal to 0. Let's look at the other functions, other important function. The next function we will encounter is basically natural logarithm of x. Or sometimes you might even ask, people will ask you to plot log of x with the base 10. ln x basically means the base is e, the exponent, and that is what is being plotted here, because this is what very often in physics and mathematics we use. So this is again a curve which tends to 0 at minus infinity. Okay. So this curve will touch the y-axis at minus infinity. Now you have to start wondering, where exactly does this point lie? That is, when will f of x be equal to 0? At what value of x will f of x be equal to 0? That is something which you will have to think about. The second thing which you have to think about is whether this function keeps on increasing throughout, or will it be approaching a boundary? That is, will this function touch this function, some line like this, at a very large value of x? So these two things I leave it to you as a homework assignment. The next function, which is of extreme importance in physics, especially when you study gravitational potential or electrostatic potential, is the function which is called as 1 by x function. Usually, physics people will be concerned only with the first quadrant, but the shape of this curve is actually looking like this, and this is basically called as an hyperbola. This hyperbola touches the x and y axis asymptotically at plus or minus infinities. Okay. So here the x-axis will be touched at when it x tends to plus infinity. Here y-axis will be touched when x tends to 0, okay, at infinity. So same way this function also can be expressed. The next function which you have to think about is basically the plot of 1 by x squared. So 1 by x squared looks like this. This has a discontinuity at x is equal to 0 because it will go up to infinity in this region. The next important function which you will encounter often in when you study kinetic theory of gases or heat or statistical physics is a function which has got a very famous shape, which is called as the bell curve. Okay. The bell curve. This curve has got multiple names. Some people will call it as a Gaussian, and others will call it as a normal distribution. Statistician will call it as a normal distribution. This bell curve is very commonly seen when you do social sciences or things related to nature. For example, if you study the IQ, intelligent quotient of people, the IQ of people are supposed to lie on a bell curve. If the population of St. Joseph's College is taken, it's supposed to lie on a bell curve and so on. So this is of extreme importance. The exact form of the Gaussian, I am showing it here. This formula is basically going as e to the power x minus mu. Mu is basically an average value. Average value basically corresponds to the peak. For example, this particular graph, the mu value is taken to be equal to 2. Okay. So x is basically the variable, mu is the mean value or the corresponding to the peak value, and sigma is going to be called as the standard deviation of the curve. That is here. If you look at this x-axis is actually plotted in terms of sigma. So this distance is basically equal to sigma. So this value is related to something called as the full width at half maximum. So if you look at the peak, okay, this peak value, so let's call that as fx max. So you'll have to find out half maximum. That means you'll have to find out where exactly does the fx max by 2 lie. You will see that fx max by 2 will be slightly different somewhere here. Okay, so this is fx max by 2, and this is sigma is related to this fx max by 2 by this particular relation. Full width at half maximum. Full width means this point, this is the full width at half maximum is going to be equal to 2 times square root of 2 ln 2 times sigma. Okay, that is the exact formula. So you will be able to find out how much is sigma. Sigma is basically this distance. So from the maximum value, this distance is going to be called as sigma. So the sigma, you can see it here. Sigma is here. So this is going to be the exact form of your Gaussian curve. Okay. So in this case, sigma is taken to be equal to 1, mu is taken to be 0. So mu is equal to 0 here. Sigma is nothing but equal to 1. Okay. So then we have neglected this 2 pi term. That should have been at 1 by square root of 2 pi here. Then it would have been exactly like a Gaussian with these conditions. but I have neglected the square root of 2 pi in this particular expression. Now, let's go to the next part. That is basically the curve which is x e to the power minus x squared. Okay? So this is again another curve which you'll encounter in uh, heat and thermodynamics, statistical physics, etc. This curve is naturally going to be an anti-symmetric curve. Okay? Again, physicists will be concerned only with this part of the equation. Okay? In the first quadrant, what it's like in the first quadrant. And finally, we have an expression which is going to be called as x squared times e to the power minus x squared. With some additional factors, this is going to be called later as Maxwell's velocity or Maxwell's speed distribution. Okay, curve. There will be some additional factors here. Then it will become a Maxwell's speed distribution. This function will be a symmetric function actually. So if you had plotted it along the x-axis of negative x direction, you would have seen a mirror image of this particular curve. So this is a anti-symmetric curve, and this is a symmetric curve. What about this one? This will be also a symmetric curve. Okay. Now, these functions are extremely important, and you should also look at what will be the integral values of these functions. Now let's go into the next important aspect, that is basically guessing the product of functions. In our case, I'm going to plot or find the product of two important functions, f of x is equal to e to the power minus x and f of x is equal to x. So the product of these two functions, the first function which I mentioned goes like this, and the second one is basically a straight line which goes like this. So the product of these two functions are going to lie on as shown in this green curve. Notice one thing, the initial period, the function is dominated or closely aligned to the straight line, but the latter part of the curve, it is going to be dominated by the exponent part, not the straight line. So if you didn't know anything about this function also, you could have guessed that initial part of the function has to be straight line, the latter part has to be dominated by the exponent part. And if you had taken the first derivative of these two functions, that is this one and this one, you could have even guessed where exactly does x e to the power minus x lie, whether it will be above the exponent or above the f of x or in between. I mean, f of x is equal to x or in between x and e to the power minus x. And if you had taken the slope and then calculated that, you would have seen that this function has to lie above the exponent, and you would have been able to guess at the shape of this curve without actually plotting the function. Now I leave it to you another particular product that is very important, especially when you study something called as damped harmonic oscillator. So this is a cos function and this is an exponent function. We'll have to find out what is the product of these two, and when you do that, you will see that the product looks somewhat like this. So important thing for you to notice is the initial part, the cos function dominates and the function is still oscillatory, but if you draw an exponent, you will see that the amplitude of oscillation actually keeps on decreasing exponentially, somewhat like this. This is what I have plotted here, just to show you what happens. This is the exponential function. You can see it here, this orange colored one. And then you have the cos function, which is shown by the blue color. And the resultant of these two, the product, is shown by the green color. Here, what I have actually plotted is, notice this thing, I have plotted cos x I have plotted an exponential function which goes as with a multiplicative factor of 0.08. Okay, then I am finding out the product of these two. You should start wondering what happens if I had changed this part to some other value. What could have happened? I strongly urge you to plot it in that mathematical software and then try to figure out what happens when these exponent values are changed. It's quite an interesting thing to check. Another homework I would like to leave with you is basically the product of sine and an exponential decay function like this. Uh, since I have already done the plot, I'll just show it you quickly, but I will not go into greater detail about it. You people should be able to explain to me what happens here. With this, I'll stop